Welcome, everyone. Really excited to introduce our 2023 Warren K. Lewis lecturer. But first, I'm going to tell you a little bit about the origin of this lecture series, Warren K. Lewis. I would like to just say a few words about him. He is known as Doc Lewis, and he was actually known to have an enormous impact on shaping this program and the field of chemical engineering as a whole. Doc Lewis received his PhD in physical chemistry from the University of Breslau, Germany in 1908, and he joined MIT as an assistant professor in 1910. He was promoted to professor in 1914. Now, we were formed as a program in chemistry in 1888, but we weren't an independent department. It was actually in 1914 that we became an independent department led by Doc Lewis. He was the first head of that newly formed department. After this, he devoted himself to teaching research and consulting and became an influential member of the department until his death in 1975 at the age of 92. Now, Doc Lewis revolutionized the design of chemical engineering equipment with the concept of unit operations, the first paradigm of chemical engineering. He was an eminent researcher and inventor. He contributed much to the field of industrial chemistry with over 80 patents to his credit. For example, he pioneered the use of fluidized bed catalytic cracking and refining. Now, above all, Doc Lewis was a superb educator. His text, called Principles of Chemical Engineering with Walker and McAdams in 1923, first defined the discipline. His lectures are legendary for the combination of beautifully organized material and Socratic exchanges with his students. And you can see him in the middle of one of those exchanges here, very emphatically making a point. Not surprisingly, he won many awards, among them the President's Medal of Science, the President's Medal of Merit, and the Priestley Medal from ACS. As a most fitting honor, our professional society, the AICHE, has honored him with the creation of the Warren K. Lewis Award, which recognizes outstanding education in chemical engineering. The Warren K. Lewis Lectureship, established here at MIT in 1978, recognizes Professor Lewis's revolutionary impact on chemical engineering as a field by developing the concept of unit operations, first proposed by A.D. Little and William Walker. He revolutionized the design of chemical engineering processes and equipment. Throughout his career, Professor Lewis was mindful of the needs of industrial practice. Accordingly, the Lewis Lecture features speakers from industry and from academia in alternation. Now I'm really excited to introduce Doros Theodorou, Professor of Chemical Engineering at National Technical University of Athens. His research focuses on the development of new computational techniques for understanding and predicting properties of materials based on their chemical constitution, with emphasis on synthetic polymers and zeolites. He has authored and co-authored more than 160 research papers, 26 chapters in books and review articles, and the book Simulations for Polymers and Diffusion in Nanoporous Solids. He represented Greece to the Mobility of Researchers Program of the European Union and was a member of the National Council of Research and Technology of Greece. Now, I tried to find a young picture of Doros. I could not find the youngest, but this is an earlier picture of Doros. And he always has had this glorious head of hair, so you still have that. Doros Theodorou was born in Athens, Greece in 1957. He obtained a diploma in chemical engineering from National Technical University of Athens, NTUA, in 1982. In September 1981, he started his graduate studies in the Department of Chemical Engineering here at MIT. And he first earned a Master's of Science degree in 1983 with Professor ChemE on zeolites. And then he went on to do his PhD with Professor Uli Suter in 1985. After fulfilling, I should mention, as a matter of fact, that his thesis, shown here, focused on molecular modeling of polymeric glasses. And this was actually a very unique concept at the time. And in fact, the paper that came from this work, one of the papers that came from this work is so seminal that it is still the most highly cited paper for Professor Uli Suter. And I think this really speaks to the impact of Doros's work from the very beginning of his career. After Doros fulfilled his military duty in Greece, he started his academic career as an assistant professor of chemical engineering at the University of California, Berkeley in August 1986. There, he was promoted to associate professor in 1990 and became full professor in 1994. In parallel, he was associated faculty at the Center for Advanced Materials at Lawrence Berkeley Laboratory, where he directed a new research effort on polymer surface interactions. Now, in 1995, he relocated to Greece as professor of chemical engineering at the University of Patras, an adjunct faculty member at ICE HT Forth, which is the Institute of Chemical Engineering Sciences, a foundation for research and technology, Hellas. This is actually a picture taken with our colleague George Stephanopoulos when George went to visit there, along with additional colleague Elkis Pyatakis. So this is actually a picture from that time at Patras. Now, in parallel, he was a collaborating researcher at the Institute of Physical Chemistry of NCSR Democritus. In 2002, he moved from Patras to Athens as professor in the School of Chemical Engineering at NTUA and director of the Computational Materials Science and Engineering Group. Throughout his career, as you know, he has used molecular simulations and modeling to help us understand more about polymers. This is an example of one of his seminal textbooks that I mentioned earlier, and has contributed greatly to the field of understanding these systems. And he's been recognized for that work with a number of awards. He's been recognized with the Presidential Young Investigator Award of NSF, the Science Award of the Bodasakis Foundation in Chemistry, the Dankworth Lectureship of AICHE, the D. Medema Award of the Dutch PTN, the Bird Stewart and Lightfoot Lectureship at University of Wisconsin, the John M. Prosnitz Award of PPE-PPD, the DSM Lifetime Achievement Award, the European Federation of Materials Sciences European Materials Medal Distinction, and the John M. Prosnitz AICHE Institute Lecturer. And in 2015, he was also elected a member of the National Academy of Engineering. He has had an incredible career, and we're very excited to hear more about his work. So let me turn things over to Doros directly. Thank you, Doros.
Thank you very much for this excellent introduction. It is really a pleasure for me to be here, and I thank you for your excellent hospitality. So I'm deeply honored to be giving a lecture in the name of Doc Lewis, the father of chemical engineering. Doc Lewis had very diverse interests, and one of his interests was soft matter. He wrote a textbook on industrial chemistry of colloidal and amorphous materials, along with Squires and Broughton. And in the preface of the 1941 edition of that textbook, we read about the significance of getting insight into the underlying phenomena for designing processes and materials, and also the importance of nature and effects of intermolecular forces and surface phenomena for the behavior of these materials. These are themes that up to now, until now, are very important for us. So what we will try to discuss this afternoon is how one can go from the chemical constitution of a polymeric material to its macroscopic properties. We will first talk about the challenge of multiple length and time scales in polymers, and then we will see some examples of calculations of polymer properties. We'll start with polymer melts, because we process polymers typically in the melt, and there we will try to predict packing, entanglements, and rheological properties. Then we'll go into polymer glasses, and we will try to address elastic constants and the very slow process of structural relaxation in a glass. And we will finish with semicrystalline polymers, trying to predict morphologies that develop during the machine direction orientation process. So when one tries to capture the properties of polymers and materials in general, one is faced with a serious challenge, namely that these properties are governed by very broad spectra of characteristic times and length scales. If we speak of an amorphous polymer, we have structure at the level of individual bonds and radii, which is typically angstrom. We have structure at the level of the statistical or Kuhn segment length, defined such that the entire chain can be envisioned as a random walk of such segments. For typical flexible polymers, this length scale is on the order of nanometers. We have structure at the level of the entire chain, typically quantified through the radius of gyration. And for usual molecular weights, this can be 10 nanometers or longer. And we may even have phase or microphase separation phenomena leading to domains with characteristic sizes of 1 micrometer or larger. Even broader is the spectrum of characteristic times that one has in polymeric materials. Bond vibrations have periods on the order of tens of femtoseconds. Conformational transitions, gauche trans-isomerization, for example, in a polyethylene melt, has waiting times on the order of tens of picoseconds. Longer and longer sequences of chains take more time to conformationally isomerize until we come to the longest relaxation time in a melt, that is the time required for a chain to diffuse by a length commensurate with its size and forget its previous conformation. And for even modest molar masses, this can be longer than milliseconds. If we have phase and microphase separation phenomena, these have characteristic times of seconds or longer. And when we go to the configurationally arrested glassy state, the very slow process of physical aging, whereby the properties of a polymer change with time, may have characteristic times of years, 20 degrees below the glass temperature. So from bond vibrations to physical aging, we have something like 21 orders of magnitude, and clearly one single modeling approach would not be sufficient to address all this. By comparison, atomistic molecular dynamics, that is tracking the temporal evolution of a molecular model by solving the equations of motion for all constituent particles, can take us to microseconds on typical clusters that we have in our laboratories, or it can take us to milliseconds on special hardware, but it can certainly not address this entire spectrum from femtoseconds to years that we encounter in most physical, chemical, materials, and biological systems. What do? We resort to multi-scale modeling. We develop hierarchical modeling and simulation methods, which consist of many interconnected levels, from the electronic to the atomistic to the mesoscopic to the continuum, each level informing the more coarse-grained ones, such that we can ultimately bridge what happens at the electronic level to macroscopic properties with a minimum of adjustable parameters. Here we will talk primarily about atomistic and mesoscopic modeling, the boundary between the two being set rather arbitrarily at 10 nanometers and 100 nanoseconds. So let's start with the problem of equilibrating polymer melts and getting properties of these melts through simulation. As we mentioned, molecular dynamics falls short of the longest relaxation times of these melts if the molecular weight is very large. So since early times, our group has focused on Monte Carlo simulations to accomplish this equilibration. And what has been particularly useful is these connectivity altering moves. For example, think of two chains running near each other in a bulk melt. One can have a move which excises a trimer segment from the blue chain and a trimer segment from the red chain, and subsequently builds two trimer bridges between the pieces that have remained, so as to give us two new chains of exactly the same molecular weight, but of very different conformation. This kind of move can rearrange the long-range conformational properties in a dense melt state very effectively, so we use it in order to equilibrate long-chain polymers. And as an example of a result that one can obtain from this, I show you results from simulations of polyethylene melts. We have a box with periodic boundary conditions filled with segments of polymer chains. A chain may look like this. This is a C6000 chain. We use a force field for the representation that has been validated for small molecular weight alkanes. We completely equilibrate the polymer at all length scales under 450 and 1 bar, and we can calculate, for example, volumetric properties. Here we see the specific volume, the inverse density, as a function of chain length for the homologous series of polyethylenes under these conditions, and we see a hyperbolic dependence as is experimentally observed. And we can also predict the packing of molecules in three-dimensional space. For example, this is a static structure factor, as one obtains by X-ray diffraction, and it exhibits a first peak, the amorphous halo, that is mainly of intermolecular origin, of correlations between carbon atoms on different chains, and some subsequent peaks at higher K values, which are mainly due to the bonding along the chains. And both are represented quite well in comparison with experiment. The fact that we can equilibrate very long chain polymers gives us access to entanglements. So we can start from a well-equilibrated atomistic polymer configuration, such as this one. This is polyethylene. And then we can subject it to topological analysis to identify entanglements in three-dimensional space. Our group and other groups have developed algorithms for such topological analysis. I show you here the results from CRETA, contour reduction topological analysis. This fixes all the chain ends in the system and proceeds to reduce the diameters of the chains and the contour lengths of the chains in such a way that two chains cannot cross each other. So during the ultimate stages of this reduction process, you see that from the initial atomistic system, one gets a set of zigzag lines coming together at topological constraints of coordination number 4. So these zigzag lines are our picture of the so-called primitive paths of the chains, a term coined by Sam Edwards, and the topological constraints are our picture of entanglements. So one can go into the reduced structure and analyze the statistics of these entanglements. From the mean length of the primitive path, one can calculate this quantity here, the Kuhn length of the primitive path, or the entanglement tube diameter, and also this ME, which is the molecular weight between entanglements. So here we see characteristic values for 4 polymers, polyethylene of 2 different molecular weights, polybutadiene, polyethylene terephthalate, atactic polystyrene. We have the ME values and the entanglement tube diameter values, and they are being compared, the blue symbols are from the topological analysis, against estimates from rheological properties by Lou Fetters, and by and large you can see that the agreement is not bad. Also, the last column contains what is called the packing length. This is a measure of how fat the chain is in relation to how stiff it is. It is calculated from the molecular weight, the mass density, and the mean squared radius of gyration. And we see that that too is quite well captured, which means that the simulation results confirm an empirically proposed correlation between the molecular weight between entanglements, the density, and the packing length to the 3rd power. How could we predict rheological properties? We need to get rheological properties. To do so, we will try to capitalize on our ability to relax, to completely equilibrate polymers, and also to calculate or quantify their entanglement structure. But we really need to look at dynamics. And we cannot address this with molecular dynamics because it cannot go to very long times. So we resort to coarse graining, and it is a rather bold coarse graining that we invoke in this kind of work. We map the atomistic chains onto sequences of beads and springs, and each bead here may stand for something like 50 skeletal atoms of the detailed chain. In addition to these springs that represent strands connecting the beads, we have slip springs, A slip spring is really connecting two segments on two different chains and aims to represent the effect of entanglements. So following recent literature, we assume that these slips, the ends of these slip springs, can execute slipping motion around the chains to which they belong. This slipping motion is represented in our case as a sequence of jumps of the slip spring ends between successive segments of their chains. And we need rate constants to describe this jumping process. If a slip spring end reaches a chain end, then the slip spring may choose to slip off the chain, and so the entanglement is destroyed. However, new entanglements are created every time by chain ends as they seek to engage with surrounding chains. So there is a dynamical equilibrium. Technically, this is a grand canonical simulation with respect to the slip springs and canonical with respect to the chains. So we need an effective potential to parameterize this mesoscopic simulation approach. It is a Brownian Dynamics kinetic Monte Carlo approach. Brownian Dynamics is used to move the segments in three-dimensional space, and the Monte Carlo, the kinetic Monte Carlo, is used to introduce these jumps of the slip springs along the chains, and also the creation of new slip springs by the chain ends. For the bonded interactions, we simply invert correlation functions obtained from atomistic simulations to get effective bond stretching and bond bending potentials. For the non-bonded interactions, we really introduce a local density-dependent non-bonded free energy density, which is based on an equation of state, in our case, the Sanchez and Lacombe in most of these calculations, which is consistent with the volumetric properties of the polymer. We also need some parameters for the dynamics. We need a friction factor for the beads. This we obtain from atomistic simulations by looking at self-diffusivity or Rouse modes, for example. And we also need a hopping rate constant for the hopping of the slip spring ends along the chains, and that can be related to the bead friction constant. So if one employs this mesoscopic approach, which is roughly by 3 orders of magnitude faster than molecular dynamics, one can attempt the prediction of quantities such as the zero shear viscosity as a function of molar mass. This is shown for polyethylene under these melt conditions. We have a set of results from equilibrium Brownian Dynamics kinetic Monte Carlo. These are the green points, and a set of results from non-equilibrium Brownian Dynamics kinetic Monte Carlo of the melt being sheared. The results from the equilibrium and non-equilibrium agree with each other. And overall, we're quite happy that these results are consistent with the scaling of the zero shear viscosity with molecular weight, that for long molecular weights in the entangled regime, eta 0 goes like molecular weight to the 3.4 power. Down here, you can see also results from atomistic molecular dynamics with the blue triangles. Necessarily, they are confined to small molar masses because the relaxation times are manageable by molecular dynamics only there, along with the experimental measurements. One can also try to calculate the viscosity itself as a function of the shear rate. And here, instead of the shear rate, we use the Weissenberg number, is the shear rate times the longest relaxation time of the melt. And for various molecular weights, we see this prediction for the eta as a function of the Weissenberg number. We see that for low Weissenberg numbers, the eta plateaus to a value that is what we call eta 0. We have the Newtonian plateau. But for large Weissenberg numbers, for strong flows, we see that there is a pronounced shear thinning behavior in these melts. That is well known. And the exponent that expresses this dependence on the shear rate or on the Weissenberg number is minus 0.7, close to what is measured experimentally. Of course, the simulation also tells us why there is this shear thinning behavior. Why do we observe these nonlinear rheological properties? These here are distributions of the end-to-end distances of the chains in the melt when subjected to flows of different Weissenberg numbers for 2 different molar masses. We see that for low Weissenberg numbers, the chain conformations are pretty unperturbed. What we get here for the distribution of the end-to-end distances is close to a Gaussian distribution. However, for strong flows, there is a pronounced unraveling of the chains. The end-to-end distribution becomes much broader. Shown here are the orientational tendencies of the chains as a function of Weissenberg number. We have the second Legendre polynomial formed from the angle between the end-to-end vector of a chain and the three coordinate axes, x, y, and z. We see that for weak flows, for Weissenberg smaller than 1, the orientation is random. This P2 is equal to 0. However, when the flow becomes strong, there is a pronounced tendency for the end-to-end distance or vector to orient parallel to the x-axis of the velocity and normal to the y and z axes. In fact, there is a small difference between the y and z axes, which leads to what is called the second normal stress difference for these sheared melts, which is captured quite well by this mesoscopic simulation approach. We can also calculate the storage and loss moduli for melts which are subjected to oscillatory shear deformation. G prime and G double prime, they express the elastic and viscous response of the melt to this deformation. So here we see these results. They were obtained essentially by calculating first the stress relaxation modulus from the time autocorrelation function of the stresses, and then Fourier transforming it to get G prime and G double prime. The red symbols are the simulation for G prime with the filled and for G double prime with the open symbols. The black symbols are the measurement for a polyisoprene, cis-1,4 polyisoprene melt of comparable molecular weight, and the agreement is quite satisfying, especially the fact that we can calculate these G prime and G double prime at low frequencies, low omega, which are completely inaccessible by molecular dynamics. So all this concerned melts. What about glasses? We very frequently use polymers in a glassy state as structural materials, for example, or optical materials. Can we address the properties of a glassy polymer? This has a long history. Even my PhD thesis was on glassy polymers, as you heard. So in order to model glasses, we postulate or accept that a glass is configurationally arrested in the vicinity of a local minimum of its potential energy hypersurface with respect to all the degrees of freedom. The degrees of freedom, which are very many, of course, they are all the atomic coordinates. Here, I collapse them onto one axis for graphical simplicity. The potential energy hypersurface has a variety of local minima, and we assert that a glass fluctuates in the vicinity of such a minimum within a basin that is formed around this minimum. For a two-dimensional representation that perhaps shows the hypersurface a little better, I show you this plot here by Chris Delago. Some of these basins may be communicating over relatively low minima, which can be traversed at the prevailing temperature. So we may have meta-basins in the multidimensional configuration space of the system. However, meta-basins are separated by very high barriers which cannot be overcome at the prevailing temperature, so the system is configurationally arrested. The distribution among the different minima is governed by the history of formation of this glass. So when we measure the properties of a glass, we essentially measure arithmetic averages of the individual properties of these basins. These are arithmetic or quenched averages as opposed to Boltzmann-weighted averages, because there is a restricted equilibrium established within each basin. So our first concern is to create such minima of the potential energy with respect to the microscopic degrees of freedom, and we do this by taking a well-equilibrated melt and quenching it down to low temperature to form a glass. While the melt is confined inside the local minimum, we will invoke a quasi-harmonic approximation. That is, we will expand the potential energy in powers of the mass-weighted coordinates. The first term is 0 because we're working at a minimum. This Hessian matrix of the second derivatives with respect to the mass-weighted coordinates plays a very significant role because its eigenvalues can give us the normal modes of vibrational motion around the minimum. So the square roots of the eigenvalues at the minimum give us the normal mode frequencies. And from each normal mode frequency, we can calculate a corresponding vibrational partition function. So as long as the system is confined in the basin, it can be described by a local thermodynamics, where the Helmholtz energy is the sum of the minimum energy, the inherent structure energy, plus the vibrational contribution due to all these modes. We have a fundamental equation essentially for the system confined to the basin, and we can use it in order to estimate properties. It is important to realize that both the inherent structure energy and the angular frequencies that go into this expression are functions of the spatial extent of the system. If I change the dimensions of the box, they change, and therefore I can learn about the volumetric and elastic properties of the system. So let's look at some volumetric properties first. Here we have atactic polystyrene with a model that was proposed by Alexei Lulin some time ago. And based on this quasi-harmonic approximation on the expansion that we showed, we calculate the specific volume as a function of temperature under atmospheric pressure. There are results from both the quantum mechanical and the classical treatment of the vibrational motion. At these temperatures, they are practically identical because the temperatures are quite high. And we see that they produce an expansivity which is significantly lower than in the melt state, where we can calculate the volumetric properties by molecular dynamics. So we get this change in slope of the volume versus temperature curve that is associated with the glass transition. And in this particular case, the model is good, so agreement with experiment in terms of volumetric properties is quite good. These are results from averaging over 5 basins. One can also calculate elastic constants, taking into account the thermal motion as well. So to do so, one takes the model and subjects it to uniaxial tension or compression deformations in the x direction, having the y and z directions exposed to 1 atmosphere pressure. And from these deformations, one can calculate the stress-strain curve, which is shown here. And for the imposed stresses, it is linear. We're in the elastic regime. And one can see also the temperature dependence of the stress-strain relation. The higher the temperature, the softer the material becomes. So here we see the Young's modulus and its temperature dependence as predicted by deforming 200 such computational specimens confined in the minima. And also from the lateral contraction or expansion of the specimen, we can calculate the Poisson ratio and its temperature dependence. And overall, we can see that these are not bad when compared to experiment. Now, can we deal with this process of relaxation of the system slowly changing its properties as time goes by, because glasses are not in thermodynamic equilibrium? What we can do is we can start from a minimum, and we can access as many as possible saddle points leading out of this minimum in the multidimensional configuration space of the glass. And having calculated such a saddle point, we can tumble down into an adjacent minimum by a steepest descent construction. So we can have trajectories which take us between adjacent minima or reaction paths. And for each such reaction path, we can calculate through harmonic transition state theory rate constants for going from A to B and from B to A. This, of course, can be done also for other minima that are connected to the original minimum, or for minima that are connected to the original minimum. So in the end, one can sample a network of connected minima and atomistically calculate the rate constants of these connections. This is an example of such an elementary transition from minimum to minimum. It is atactic polystyrene, a rather simple small system, and we have a transition from the original minimum to a new minimum, which, as you can see, is accompanied by subtle motions, cooperative motions of the atoms in the system. This is the energy profile of the movie that we just showed previously. So indeed, we go from a minimum into another minimum across a maximum, because here we have collapsed the configuration onto the Euclidean norm of the position vector of all atoms. And in this particular case, you see that this barrier is approximately 4 kT. So one can do this over and over again. One can start from a minimum and sample many other minima connected to it. And in this graph that results, I distinguish between what we call explored states. These are the ones shown in blue. These are states for which we have calculated as many as possible paths leading out of them. And boundary states, the black ones, these are states which are connected to explored states, but not yet explored themselves. In the beginning, one starts with a small set of explored states. As time goes by, one has to augment this set. So one takes one of the boundary states according to the fluxes leading into them and explores it, which means that it joins the rest of the explored states and its neighbors become boundary states. So in the end, one has this very rich connectivity among basins, which is represented graphically here. So having this set of states, one can try to solve the master equations for the probability of occupancy of these states. Assume that we start with the system being in a given state, for example, in this red point, and we want to really watch the system diffuse out into the rest of its state space. This is the master equation. It tells us that for each of these states, the probability of occupancy changes with time as a result of influx of probability from other states. This is this term, and efflux of probability into other states. And for the boundary states, the black dots here, we use absorbing boundary conditions. So we have devised an algorithm for solving the master equation in such a network that is progressively augmented on the fly with the absorbing boundary conditions on the boundary states. And one can sort of watch this probability diffusing out from the original point here. We have sort of a diffusion of probability outwards as time goes by. Red here means high probability, blue means low probability, and you can see how the system, as time goes by, really visits more and more states in its configuration space. This can be taken out to something like 1 millisecond. That's where this will actually end. And we see that many states are actually being visited. Some of them are not visited so much, and the probability distribution becomes broader. So having done this solution of the master equation, one can look at some features of the temporal distribution of this situation. One thing that one can look at is the probability efflux into the boundary states as a function of time. And I show you this for different sizes of the set of explored states. Initially just one state, then 10, 100, 200, 300, 600, etc. So remarkably, one observes that if the set of these states is large enough, this efflux of probability into the boundary states as a function of time stabilizes at a certain shape, which is characterized by the presence of well-characterized maxima. There is one, for example, this is polystyrene at room temperature. There is a maximum at 10 to the minus 10 seconds, and another one at 10 to the minus 6 seconds. So these are characteristic times that one can bring into a logarithm of relaxation time versus inverse temperature plot. And here they are. These cyan points are the characteristic times from the calculation we showed earlier. If we repeat the calculation at different temperatures, for example, 250 or 200 Kelvin, we see these characteristic times. And it is obvious that these times are representative of some molecular processes happening inside the glassy polymer. And it seems that they are representative of what the experimentalists call gamma and delta subglass relaxation transitions. These are accessed by dielectric spectroscopy and also neutron scattering experimentally. In the same plot here, we show what happens in the melt state at high temperatures. Here we have again relaxation times, these purple symbols that were obtained by direct molecular dynamics by looking at the reorientational motion of phenyl stems in the melts. And they give us a picture of the alpha or main relaxation transition. And we see that with a combination of this landscape-based picture with molecular dynamics, one can access relaxation both inside the melt, in the glassy state, and in the melt state. And results seem to be quite promising when compared against experiment. Now let's go to a final example that has to do with semicrystalline films. We use polyolefin films as packaging materials, and nowadays there is a strong motivation to move from multi-layer packaging materials to single-layer and single monomaterial packaging. In these packaging applications, we of course rely on the semicrystalline morphology that develops and prevents small molecular weight penetrants like oxygen, etc., to penetrate the film. So we will try to simulate at the atomistic level with molecular dynamics the process whereby such films are formed. These are formed by the so-called machine direction orientation process. Here comes the polymer, the film in. It is preheated, and then it is subjected to drawing in these drawing rolls, which move at different velocities. And the draw ratio can be from 2 to 1 to 10 to 1. The whole thing, after this, it comes through annealing rolls, which stabilize the film, and then cooling rolls. And the draw ratio can be quite high. The production speed is quite high, 300 meters per second, and the drawing temperature is below the melt temperature. World-leading work on crystallization of polymers is done here in Professor Rutledge's group, and we try to follow their footsteps in simulating specific stages of this process, namely the drawing stage here and the annealing stage. How do we simulate those? For the drawing stage, we take a melt sample, an isotropic melt sample. We bring it to this sub-TM temperature, and then we subject it to a deformation with non-equilibrium molecular dynamics that pulls it in the X direction, keeps in the Z direction rather. It keeps the X direction constant to sort of emulate this film geometry, and it exposes the Y direction, top and bottom, to atmospheric pressure, so the film shrinks in that direction. The deformation is imposed with a specific true strain rate, epsilon dot, and as we mentioned, Lx is equal to Lx0, it's constant, and sigma Yy, the stress in the Z direction, is -1 atmosphere. As regards now the annealing simulation, we take this film that resulted from the drawing, we keep it under constant stress in the Z direction, the sigma annealing, and we again keep the X direction constant, and the stress in the Y direction is -1 atmosphere. So let's look at some movies of some very simple simulations on a very small system. This is 8 chains of C1000, a rather small system, at 350 Kelvin and at an epsilon dot of 10 to the 7th inverse seconds, quite high. And here we have tried to differentiate ordered regions, which will appear purple, from the amorphous regions, which are blue. If you look closely, you will see that some purple regions emerge and then they dissolve again. This is fluctuations leading ultimately to a nucleation phenomenon. So we will see that an ordered phase, an ordered nucleus appears and rapidly spreads through the system. And since the system is very small, here it is, the nucleus, the growth process ultimately percolates the model system in both the X and the Y direction. So finally, one gets a semi-crystalline morphology where one has lamellae, like this one and this one, and in between one has amorphous material. So one can take this semicrystalline morphology and try to calculate the degree of crystallinity. And in doing so, we have adopted methods that were proposed by Yamamoto. One partitions the system into voxels or cells of dimension equal to twice the sigma, the Lennard-Jones sigma of the methylene. Within each such cell, one calculates an order parameter from the angles theta ij between different chords in that cell, a chord being the straight line segment that connects the midpoints of two adjacent bonds. And according to Yamamoto, when this P2 is larger than 0.7, one can classify the cell as being crystalline. Otherwise, it is amorphous. So based on this definition, here's how the crystallinity, the degree of crystallinity, evolves with a stretch ratio during this drawing process that I showed you. Originally, it is 0, and it remains so during a long incubation period. But then one has nucleation and growth of the crystalline lamella, leading to something like a 0.45 crystallinity in the ultimate system. One can adopt a different criterion for crystallinity, for example, work with the enthalpy rather than with orientation. One can take the enthalpy of the simulated system and subtract from it the enthalpy of an equal amount of melt, according to the molecular model used, divide by the mass, and also divide by the specific enthalpy of fusion, and that way calculate the calorimetric, so to speak, degree of crystallinity. This is shown with these very rapidly fluctuating black lines, and by and large it is consistent with a structurally calculated one, the red line. So these would be two different simulation approaches to calculating crystallinity that are sort of analogous to calorimetry and X-ray diffraction. At the same time, one can also track how the entanglements in the system evolve upon the emergence of these ordered regions. Originally, the system has entanglements throughout, and these kinks are the entanglements. But then when it starts crystallizing, you will see that the primitive paths become very elongated where the crystalline regions are. The kinks are pushed into the amorphous region, and one can even count the entanglements and see how they behave against the stretch ratio. This black line is the total number of entanglements, because some entanglements really flicker. I mean, they are not permanent, whereas some we classify as long-lived because they survive throughout the simulation. And what this seems to indicate is that the total number of entanglements goes down. The long-lived entanglements go down by just a little bit. And in the end, in the semicrystalline film, one has only long-lived entanglements, which have populated this middle amorphous region in the film. So one can even try to estimate the crystallite size, or the lamellar size, in these ordered materials. From this, with Yamamoto's criterion, we take an atomistic structure and we convert it to what we call the Tetris plot. That is, we have crystalline and amorphous regions only in the system. And then we conduct a clustering analysis. For example, for this kind of configuration, one identifies 4 such clusters. And for each cluster, one can calculate the dimensions that it has. The cluster analysis indicates a dimension for the finished semicrystalline morphology of roughly 19 nanometers, which is not too far from what experimentalists report, but for polyethylenes that have been crystallized under quiescent conditions. Now let's look at a movie of a larger system, 100 C1000 chains, subjected to a lower deformation rate, 10 to the 6th inverse seconds. We see that we have the emergence of 2 nuclei here, which are of roughly a circular projection, and the degree of crystallinity really starts rising at a stretch ratio of roughly 1.25. If we continue with this crystallization, we see that these crystalline regions grow, and they grow in a rather anisotropic manner. They become more elongated, such that the projection is more elliptical than circular. The growth happens diagonally at approximately 40 degrees, and the degree of crystallinity continues rising, but at a lower rate than originally. We go even further, and we see that the flow really starts deforming these two crystallites that have formed, and the degree of crystallinity keeps at a certain value. And interestingly, if we deform even further, then we see that there is secondary crystallization here. There is another ordered region that appears that did not exist originally, and the crystallinity starts rising again. And if we continue even further, then we see that this crystalline region grows, and there is even a reorientation of one of the original crystallites. Let me play this. So we get more secondary crystallization here, and this thing rotates in some way and ultimately percolates the entire film. And there is even more, I guess. Okay, so you see that ultimately there is a quite complex morphology that involves these crystalline regions dispersed in the amorphous region. And one could envision that through such simulations, having the morphology, one could calculate the tortuosity that such a structure would exhibit to a small molecule trying to go through the system, and therefore the permeability. Of course, it would be very advantageous if such calculations could be conducted in a coarse-grained sense to be able to look at smaller deformation rates and larger systems. So to leave you with some conclusions, there is a tremendous challenge associated with long times and length scales in polymeric materials, and this can be met through the design of carefully planned statistical mechanics-based multi-scale modeling methods. We have seen that connectivity altering Monte Carlo is quite useful for fully equilibrating melts of large molecular weights at all length scales, and also conducting topological analyses in order to learn about the density of entanglements in these melts. Now, based on this kind of information, one can design hybrid particle field mesoscopic simulations which employ slip springs to represent the entanglements. These are by roughly 3 orders of magnitude faster than molecular dynamics, and one can try to capture the linear and nonlinear viscoelastic properties of melts. In the glassy state, one can calculate volumetric properties, elastic constants, even plasticity that I did not show, but challenge is to calculate the structural relaxation that a real-life glass would exhibit as a function of time. And here, this landscape picture of a multidimensional potential energy landscape with many minimine basins between which the system can execute infrequent transitions seems to be quite useful. One can design an algorithm that solves the master equation for the population of probability in these basins in a network that is augmented on the fly, and track subglass relaxation transitions apparently in agreement with experiment. And for ordered systems, for systems which crystallize, one can try to perform non-equilibrium molecular dynamics to see how the morphology of these systems can evolve at given conditions of deformation rate, epsilon dot, and temperature, and see how the semicrystalline morphology develops. That would be very important for permeation and mechanical properties. Finally, I would say that seamless connections between the electronic, atomistic, mesoscopic, and continuum approaches, nowadays aided by machine learning, are leading to practical computer-aided materials design tools which are applicable in an industrial setting. I would like to thank my collaborators who did all this work, those who supported it financially, and you for your attention and patience.
Thank you so much, Doros. And before we start Q&A, I would like to present to you the Warren K. Lewis Lecture Award. Thank you so much for your incredible scholarship.
Thank you very, very much. I'm deeply honored. Thank you very much, Paula. Thank you.
All right, the audience questions. We're open for questions. Yes, Bill.
So I was very interested in your model for the network of moving from the different basins. Yeah, and then how you had the meta basins, which are, I guess, like kinetic species.
Yes.
And I was wondering first if you could comment about how you identified when you're at a transition state in these very complicated systems. And then secondly, have you tried to make like a kinetic model? I guess your master equation is kind of like that, to actually have species and right rate constants for changes.
Yes. As you point out, this is very much like a network of chemical reactions, indeed. Now, in terms of when we are at the saddle point, this is an explicit atomistic calculation starting from a minimum and going up by Surgeon-Miller type algorithm until you reach a first-order saddle point. So you know that you are at a first-order saddle point. Of course, you do this as many times as you can. There is a tremendous number of saddle points. It turns out, however, that most of those are very high in energy, so they would not be accessed. So if you do this again and again and again, you ultimately end with this rather small set of saddle points that play a role for the temporal evolution of the system. Yes, you asked, please remind me the second.
Can you convert this back to a kinetic model and extract phenomenological rate constants connecting these kind of species that are the metabasins?
Yeah, in fact, something that we can do is something analogous to lumping, for example. I mean, after a while, it will not pay to have all these individual species. It is much more, effective to lump them into one species where the communication is fast and see how that is connected to other metabasins. And we are doing that. We call this lumping. And interestingly, what I use is the methodology of my former advisor, Jimmy Way. He had worked on lumping, and we can invoke this. Go from the chemical reactions into this. This is absolutely necessary because beyond the point you have too many states and you cannot track them computationally. So you should coarse grain. Yes.
Additional questions? Yes.
So first, Doros, wonderful stuff in so many different areas, a lot of contributions. Let me ask you about some of your latest observations on crystallizing systems. Yes. So now you have a big enough system where you're seeing multiple nucleation events, and you're getting lamellae. But when you start talking about morphology, so the dominant morphologies in polyethylene are spherulitic when you deform very little, and shish kebab type structures when you deform a lot, and nobody really knows exactly what the shish is in the shish kebab.
Yes.
So there's a good question there. But my question for you is, how do you don't see either one? I don't see either one when I look at your pictures. So how do you rationalize what you're observing?
You're absolutely right. I wouldn't say that we see certainly not spherulites and not shish kebab. I suspect that shish kebab is for a fiber drawing type of deformation. I have a hunch. At least I present this in front of people coming from Borealis, and they don't complain, that this is really what happens in the machine direction orientation process, that you get these flat lamellae, so to speak. I cannot prove this. And actually, I would love to have experimental data to compare this against. I don't. But I think this is actually what you get from the machine. Yeah, you remember, it is the machine direction orientation process. The x direction is kept constant. It cannot shrink. So I hope and think that this is indeed what is happening. But I mean, I cannot prove this.
Oh, there must be X-rays or something that would show that, right?
Yes, actually, a parallel sort of experimental project would be very welcome. And as I mentioned also, in the real machine direction orientation process, one typically starts with a system which is already partly crystallized. Here, in order to have a very well-defined original configuration, we started from the melt. But I think this is not what is done in the MDO process.
And thinking about your answer, so if you go to very high Weisenberg numbers, which I think you had some pretty high ones there, would it not begin to approach something that looks kind of like uniaxial because the strain rate in one direction is so much larger than either of the other two? One is zero, but the other one is not.
I think these rates are relatively, I mean, they are very fast, of course, but I think we are not close to such a situation. Okay. If you draw too fast, then you may get cavitation in the system. Yes. Well, this is open. If you have experimental data on this, I would love to have them.
Hi, thank you for a great talk. I'm wondering why atactic polymers is like the representative case for these studies. Like, what about other stereoregularities of other polymers?
Well, I mean, the approaches that we discussed, I mean, for the melt and for the glass are very general. We use the quintessential sort of melt, polyethylene, and the quintessential glass, which is polystyrene, atactic polystyrene, because there is so much data on these. But these are perfectly general. And in fact, they have been applied to other types of systems. I mean, for example, there were fluorinated polymers considered as sealants and adhesives that we applied this mesoscopic melt thing to. And the glassy approach has been applied to PMMA as well. And I mean, you can do it too. It's very general because it all involves probing the multidimensional potential hypersurface. All you need is a good force field. Yeah.
Additional questions? We'll pass it back. We're going in a direction here.
So I had a question about the glassy polymer stuff. So when you're exploring these different local minima, Professor Green asked about how do you identify if it's a transition state, but do you just run these MD simulations brute force, or are you like kind of blockading it as it goes up the energy barrier?
It is not an MD simulation. It is rather a search for a saddle point. I mean, the analog of minimizing. It is much faster. In other words, you try to go up in one direction to have a maximum in one direction and a minimum in all other directions. And there are algorithms, as I'm sure Bill knows very well, to do that, for example, for chemical reactions, to identify a saddle point. So that's what we do in multidimensional space. So this is relatively fast. And then you do a steepest descent to tumble down in the other direction.
Yeah, makes sense. Yeah. Thank you.
Thank you.
Yeah, I have a question about the last part of the drawing simulation. So I found the rate of increase of nucleation it will have two increase as low deformation, high deformation, and the rate is kind of different. I'm not familiar with this area, so do you have any explanation why the rate is different?
You mean between the primary and the secondary crystallization?
Yeah.
Because, I mean, the thing saturated and then it started moving again. Because I think this is probably caused by the stress that this thing is feeling. It is partly solid now, so it is crystallizing under different conditions. It is something we didn't expect. I sort of show it to you as a curiosity that this secondary crystallization would happen. And of course, we are interested in conducting this at as low strain rate as possible. Epsilon dot was 10 to the minus 6. This is, believe it or not, slow for molecular dynamics. But I mean, the real one, nobody says what it is. But I tried to estimate it from things in the literature, and it should be 10 to the minus 3 to 10 to the minus 4 inverse seconds. So we are off. But I mean, Greg, you said that perhaps it doesn't matter. I mean, the exact epsilon dot. We don't know. I mean,
I'd like to You have a C1000, so that's a pretty big browse time.
Yeah, yeah, it is very, very big, yes, yes. But I don't know that the morphology that we get depends sensitively on the molecular weight, beyond a certain molecular weight. I think we get very similar results. We were asked to do Borealis demanded that we do C10,000, so we are doing C10,000. We can equilibrate it. So. Mike.
As always, Doris, wonderful work. Wonderful to be hearing about it. I have a question that is, I think, following up maybe on where Bill was in terms of the physical aging simulations. As you're moving among, as the system is moving among these different local minima, should I be thinking of that as many minima that are all fairly similar in energy as the system moves among them? Or is this in the long run some sort of downhill motion to relax some sort of driving force and cause some sort of other kind of macroscopic change in the sample that the real sample would be showing over years? How should I be thinking about that?
It is the latter. In fact, you can actually calculate a free energy from this, because you have all the tools. I mean, you can calculate a time-dependent free energy. This is a monstrosity, of course, but and it goes down. So the system is really trying to approach equilibrium, but in an extremely slow fashion. That's what it's doing. It's moving downwards by repopulating this distribution of minima.
So in a sense, it's moving from this arithmetic average down to some sort of Boltzmann-weighted average over some sort of long time?
At infinite time, it would distribute itself a la Boltzmann. There's no question about that. But it would take infinite time. Yeah. But it's striving to assume a Boltzmann distribution. And in a very related fashion, you can also work with where does the plastic deformation start. I didn't touch upon that, but you'd really have access to, the yield point, so to speak. And that's nice. And George Voyagis has gotten that for both, stretching and compression. And they're a little bit different. Yeah.
Thank you.
Thank you.
Thank you, Doris. This was a really exciting discussion, and thank you for exposing the beauty of these systems and helping us understand them better. It's really beautiful work.
Well, thank you for your attention and for this beautiful hospitality that you offered me these 2 days. I mean, it was invaluable for me.
Thank you. And let's thank our speaker one last time.